Hello, everybody, and welcome again to this last session on trajectory prediction and trajectory and queue management. I'm Nicolas Durand, for those who have not been here from the beginning of the session for the first part. I'm professor at ENAC in Toulouse, and I will chair this session for the last two presentations. Our first talk is Martin here? Martin, are you here? Hello, Martin.
Yes, I'm here. In this moment, I have some connection problems.
Okay.
I hope, yeah, the internet will be.
Well, we hear you very well.
Okay.
Do you want me to ask Janos to run your presentation?
No, I think it.
Oh, now it's working pretty well.
So I could
share your
follow
screen?
all the presentation, so it should be working. I hope so.
So I'm going to introduce you while you do that. So Martin Lindner studied aviation technology and logistics at the Technische Universität in Dresden in Germany from 2007 to 2013. At the same institute, he then began working on projects in the field of flight trajectory optimization and flight performance modeling as a research associate until now. His PhD research focuses on the goal of making aircraft rotation schedules less vulnerable to delays. I give you the mic if you can share your presentation. I still don't see it, so. Okay, now we get it. Can you put it full screen? Yeah, that's perfect.
Okay.
So I give you the mic, and it's a.
Yeah, so thank you very much for the kind introduction, and yeah, a warm welcome to our presentation. So we are a small group of researchers mainly focusing on the optimization and prediction of aircraft trajectories, mainly for en route trajectories for the cruise phase. And we have made some investigations before to offer aircraft a more flexible aircraft space using by using some optimization corridors. And this is an approach we would like now to extend also to departure and arrivals. So here for our reference scenario, we have chosen the airport Munich. And you can see on the figure on the right-hand side all destinations of this airport. And also, what you also can see is that those destinations are located in a lot of directions. And what you also know is that the traffic is organized by some ATS routes, which concentrates more or less the traffic. And what we also know is that different aircraft types will have also their different aircraft, their different optimum vertical profile. And we would like to find some possibilities to ensure that aircraft can follow the optimum path. So you all know the current status quo at airports. So you have mostly a given route system, which are either standard instrument departure routes or some standard arrival routes. And those routes are mainly intended to deconflict the traffic and to implement some noise abatement strategies. But however, they come with some restrictions for the aircraft, which are especially some lateral restrictions, as well as some altitude restriction and some speed restrictions, which makes more complicated to the aircraft to follow its own optimized trajectory and to save fuel. So our intention here is to offer a more flexible use of the airspace by providing some corridors or some funnels, which could be in an easy way just an extension of the given standard instrument departure, for example. And in this paper or in this presentation, we set the scope that we are focusing on the design of such corridors based on some historical traffic data, as well as based on some optimized trajectories. So therefore, we consider the typical traffic flow, especially the destination directions, the given weather conditions, as well the individual aircraft performance. So we are aware that we should also consider some noise abatement and some safety assessment steps, which will later follow in this project. So this slide shows you the 3 or 4 main tasks which should be done to investigate the potential of such an optimization corridor. For the first case on the left-hand side, we are pre-processing some post-flight ADS-B traffic data and take a deeper look into the data if such optimization corridors or some corridors where aircraft follow already exist in the daily operations. And in the second case on the right-hand side, we are calculating for a flight schedule of Munich also some so-called unrestricted optimal flights using a flight optimization framework. For both cases now, we cluster the resulting trajectories and determine from these clusters some optimization funnels. And for the given flight schedule, we then re-optimize those flights within these funnels, but the aircraft is not allowed to leave such a funnel after allocated to them. And afterwards, we are assessing the flown distance and some fuel saving potentials, which we hope will result from the case 2 from the optimized trajectories. So at first of all, I would like to give you a short introduction to our reference case. Here we have data from ADS-B data from the airport Munich, which has 2 runways with independent parallel runway operations. And we have a data set from September 2019, which means the data is from before the pandemic. And overall, for the runway 26 right, which is our main investigation area because of the wind direction, we have in total 1,000 flights, which match some simple data plausibility criteria. For example, we can model continuous climb from these data points. And in total, after clustering, which I will show later, we have more than 400 flights, which do really represent our optimization clusters or optimization funnels. Here on this slide is shown short the data. So we have for all of our flights a unique trajectory ID, and to each trajectory ID there are typical data as a latitude, longitude, heading of the aircraft, the speed of the aircraft, and some timestamps included. And now we take the whole data set and do in the first step some clustering, which is we in the first step named inner clustering. So therefore we try to assign each of those trajectories to a given runway, where we use the first point or the nearest point of each trajectory and allocate the runway to this trajectory, which is nearest to this point. And in the second clustering step, we draw a circle around an airport with a radius of 100 nautical air miles. And do, can you see my mouse? So I have a small window here. So we do additional clustering where the trajectory intersects the circle, to find some trajectories which directly flying towards some en route waypoints. In the next step, we combine the inner clusters and the outer clusters to so-called preliminary clusters, and found here in this example 3 clusters. And for example, this cluster shown here has trajectories which are assigned to one cluster, but you can see that there are 2 different curve radii flown. And therefore, we do an additional subclustering, also within the B-scan algorithm. So therefore, we implement some moving windows, which follows the trajectory. And if any point of each trajectory is has a higher distance than 1 sigma of the mean trajectory, we open additional clusters. We open an additional cluster and recluster the data and iteratively find all of our necessary clusters. After clustering, we calculate the mean trajectory, which is also calculated using the sliding window technology. And for the mean trajectories, we are then able to calculate some gates along this trajectory. And we can define the height of each gate, the altitude of each gate, by the minimum and maximum altitude of the contained trajectories, and the width of each gate by estimating a distance which is less than 3 times the standard deviation of the mean trajectory. And by describing these gates, we are finally can state the total funnel, or the total funnel corridor, which is used by the aircrafts to leave the airport. Here on this slide, you can see some of our clustering results. So in the figure in the upper left, you can see the original data shown as blue dots. And in the first step, and by also applying the TB scan algorithm, we are able to exclude some outlier data. And in the figure next, you can then see the flight trajectories and clustered by 7 clusters for the runway 26 right. So which will be investigated in the next steps in more detail. In this figure now you can see all clusters for runway 26 right, and additionally the gates which are describing our optimization funnels. So I would like to break here short my methodology to the funnel, and would like to give you a short introduction to our optimization approach, how we can optimize the departure trajectories. So therefore, we use optimization framework called Toolchain for multi-criteria aircraft trajectory optimization, or short TOMATO, which is already referenced in the paper, so I wouldn't like to spend too much time in explaining this. But in short, you have an optimization framework with 3 core modules, where the first one calculates the lateral path. The lateral path is found by a grid or a mesh, where we apply a minimum cost search graph, for example, the A-star algorithm. And we can, in our framework, model different wind conditions, as well as some airspace structure, some airspace restrictions, and so on. And then are able to find the optimum trajectory shown here in black. And after finding this lateral path, we can calculate using the Koala aircraft performance model the optimum vertical profile under given target functions. And by using the lateral path and the vertical profile in our assessment module, we are able to evaluate the key performance indicators of operating costs and emissions, and take these costs to adjust our input parameters, and then are able to iteratively improve our final trajectory. So this was mainly developed for en route flights, and for calculating departure flights, we need a 3-dimensional grid, which was before in a 2-dimensional manner. So therefore, the most easiest way would be to multiply our given grid by a sector, by a set of pressure altitudes and we need then to model the aircraft which moves through this grid by using the formulas shown on the right-hand side here. And the problem, of course, here is that we do not know the current aircraft status at each of those grid points, because for the shortest path algorithm, the history is not known during the graph exploration. So therefore, we need some assumptions for the actual flight performance of the aircraft. And we take here some tabulated aircraft performance data from Beta, where we have for several aircraft types a set of flight performance parameters, which can be used to fill in these formulas and to calculate fuel burn and the flown distance for the optimization model. We then decided to develop a 3-dimensional grid, which builds up based directly from the aircraft performance. So we start at the runway shown here in blue at point 1, do a takeoff run until point 3, and after the runway threshold, we have a short straight climb segment until point 3. And from there on, we are able to make some turns, which is defined by a turn angle parameter. And we then trying to climb upwards to our given altitudes, shown here by this circle, until we reached the final desired destination or the desired cruising altitude. We limited the number of turns by a so-called standard rate of turn, which is 3 degrees per second. So here in the figure in the middle, you can see just as an example for the airport Munich, such an optimization grid. And on the right-hand side, you can see therefore also the 3-dimensional modeled wind data, which is in our case from the global forecasting system. After calculating this 3-dimensional path, we calculate the optimum vertical profile based on this path. And therefore, you can see here on the right-hand side in red, the assumed aircraft performance data from Beta for our grid design, and in blue, our aircraft performance model, Koala. And you can see that both lines are very similar to each other, which means that our aircraft performance assumptions made during the path search are very similar to the later results of the final trajectory. Of course, after calculating the traffic data clusters as well as these optimization funnels, we need an additional grid, which is here called a tube grid. And the tube grid is very similar to the grid shown before and uses the same flight performance assumptions. But however, here we use only the calculated gates from our mean trajectory as grid points. And the resolution is in lateral alpha and in the vertical beta. After that, we do some optimization runs. The first one is the free optimization, where we calculate a large flight data set to determine and to derive our optimization funnels. Therefore, we here use also the given flight destinations from the Munich flight schedule from September 2019, and allocate all flights which are intending to flying to the north and to our runway 26 right. And of course, we vary the takeoff mass of the aircraft as well as the aircraft type, and especially weather scenarios, to bring more uncertainty into the data and to ensure that the derived optimization clusters will be able to give the possibility for a lot of aircraft configuration possibilities to fly always their own optimum. After calculating those optimization funnels, we recalculate using the tube grid our trajectories. One in the case one for the ADS-B data, and second for the optimized funnels, and will then assess the flight efficiency as a result. So here on the left-hand side, you can see the already shown flight trajectory clusters, which are from the ADS-B data, showing here especially the structure of the standard instrument departure routes. And on the right-hand side, you can see the result of our optimization from the freely optimized trajectories. And of course, we have some points to discuss on these figures. Especially, we calculate a high number of different clusters. Mainly, this is because in the nature of this free optimization, so an aircraft is able to follow each direction and chooses the shortest distance to destination. And of course, we need in a later step some investigations to decrease the number of sectors, the number of optimization funnels, to deconflict the traffic. And another point what we found is that the size of the gates of each of our ADS-B data clusters are very small in lateral manner, but in a vertical manner we can also already find such an optimization corridor. In our optimized scenario, of course, the size of these funnels is much more bigger, greater. So to summarize the key results here, we already showed that we are able to derive from some ADS-B data some optimization funnels, as well as we can calculate some optimized trajectories and derive with the same algorithm similar funnels. And we can fly through the funnels to ensure some predictability for the ATC. And can, if we use our optimized funnels, show some fuel saving potential, which is shown here on the left-hand side. So we have here a very small potential of approximately 0.4% of fuel burn until the destination. So of course, this fuel saving potential seems to be very low, but we just optimized only the first half of the full climb procedure and compared it to the fuel burn of the whole flight. So it is very low. And if we reduce our focus, not until the destination of this flight, so fuel savings in a typical range of 1.6% are possible, which is of course in a typical dimension of some operational fuel saving measures. So our next steps in this project will of course be to include some noise abatement strategies and the consideration of noise. Therefore, we have implemented the European ECAC DOC 29 calculation methods to estimate the noise for departure and arrivals, but haven't until yet recalculate our trajectories. And as we have only considered, we also need to consider, as we have only departures considered, we also need to consider some arrival flights. And after that, we need a coupling of the whole traffic scenario and investigating how we could separate the funnels to overall deconflict the air traffic. So that's it. I thank you for your attention. If you have any questions, you can ask us. The whole team is my back. And if you would like to have more technical details, you can also have a look into the paper. Thank you.
Thank you, Martin, for your presentation and all the details you gave during it. So if you have questions, you should write them down or raise your hand or do something so that I can either give you the mic or read your questions. I don't see any right now. Yeah, there is one. So a question from Marie Carré, who liked your presentation and who would like to ask you if your research method is adaptable to arrival, considering continuous descent, for example, to reduce the holding vectoring and reduction, and to have a reduction of environmental impact. So have you considered the other problem, like on the arrivals?
Yes, of course. You can also use the shown departure grid also for arrivals by just flying reversely, but it should be no problem. However, the algorithm is only here performant if you use just the continuous descent methodology. So if you would like to implement also some level flights, the complexity of the algorithm increases very high because you have to generate a lot of grid points. So of course the methodology is usable also for arrival flights and is also intended to do in a later step.
Thank you for your answer. We have another question from Hasni Idris. Did you look into the reason behind the clusters in the track data? For example, are they caused by aircraft performance or congestion? Did you correlate clusters with aircraft types? That's an interesting question, actually.
Okay, mainly the clusters showed here are based, of course, due to the lateral path. So we considered also different aircraft types and the different aircraft performance, but it is shown more within the cluster. So the trajectories widen up this optimization funnels due to different aircraft performance, but we didn't find that different aircraft types will result to different aircraft clusters, different trajectory clusters.
Okay. Thank you for your answer. So Marie Carré wants to ask another question. She asked the first question. She wonders if this research, thanks to a better prediction of the departure trajectories, could have, if we could have a small reduction in the separation between two departing aircraft. And then be able, for example, to have an increase in the departure capacity of an airport. I think, like in the reviews, like that you had this question of separation was raised during the reviewing process of your paper. So it would be interesting to have your answer on that subject, on that matter. So the question is,
of course,
yeah.
Yeah.
Go ahead. Go ahead.
Of course, I think it's totally possible to increase the airport capacity by reducing the separation of the aircraft if you could better predict the aircraft behavior. However, the separation between the aircraft is mostly based on the wake turbulence categories, and which is more or less a safety issue, and I'm not really sure if the better predictability of the trajectory will, of course, have a good effect on the wake turbulence categories. So I think the wake turbulence category is more strict to the separations and the better predictability of their aircraft trajectory.
Okay. Any other question? I have one, maybe a question about the whole method you're using. So what I understood is that you're optimizing the trajectories inside the funnels. And this is based on the idea that the funnels guarantee an acceptable trajectory.
Yes.
So isn't there a debate on how, like, just observing real trajectories is just a guarantee of acceptable trajectories first? Like, do the real trajectories respect all the constraints that they are supposed to Like, there might be flights that go, I don't know, outside of their protection area. We don't know. And then are those funnels optimize themselves? Like, couldn't we think that maybe the global problem is that we want to have safe trajectories that have the best cost for the airlines? And why would we stay in those funnels? Is it to comply to the existing departure tracks? But can't we imagine that maybe the observed data is not does not build optimal funnels? It's a more general questions. I was wondering why at the end you have this approach, the global approach.
I hope I got the question well. We thought about this clustering and within this on the flying within this optimization funnel, that we could be able to provide a very broad optimization space for the aircraft, but we would like to ensure that the aircraft stays within this funnel, that it remains predictable for the air traffic control, and that remains also that the whole traffic flow could be deconflicted.
Okay, that makes sense. Like, considering the air traffic controller, yeah, you want to get close to what they are used to, like keep the flows that the way they are. So I guess that's your main motivation at the beginning.
Yes,
am I right?
We would like the most optimization potential for their own optimized trajectory, just by considering also the traffic flow issues which will you have at least at high busy airports. Yeah.
Well, thank you very much for your answer. Marie Carré has another question. Maybe I can give you like the mic. I think I have this option so that she can talk to you. Plus, okay, here. Can you talk?
Can you hear me now?
Yes.
Yes.
Oh, perfect. Yeah, thank you very much for the occasion. I was just considering or just doing a remark because the wake turbulences are really, I totally agree, the safety buffer that they have, but the ATCO are always putting on top some buffers because of uncertainties and so on. And that was really a big question because it could be a very good outcomes of your research. If we could then get a good enough prediction of other departure that the assessment is really good and then that the ATCO can trust, then it could lead to a reduction of the buffer, which would mean that we could increase the capacity, which will be in certain or given airports a very good outcome.
Okay, so thank you for the comment. Yeah, that's a very good hint to look deeper into research. So we didn't thought about it, but we would consider, of course, such capacity such capacity increasement also in the later research, and we would like to come back to you later if you are interested.
Yeah, totally. And I guess a lot of airports and a lot of airlines will be really thankful for that.
Okay.
Hey, Nikos, can I say something about the question?
Yeah.
So you can really increase your capacity, but improving the prediction will you can reduce the variance in which you achieve. For example, if you want to do time-based metering in departures. So yeah, the improvement in the trajectory prediction of climbs can help you with how you meet that capacity. But the capacity in departures, as Martin was saying, is mostly dictated by other things like the weight categories, the aircraft mix that you have the airport. But of course, this can help you if you use automation to do metering, time metering, departure metering.
Okay, thanks for this this answer. Any other question? If you want to raise your hand, I can also give you the mic. I think it's more like it's somehow easier to be able to talk as well. You don't need necessarily to write it down. Otherwise, we're almost at the end of the time we had. So I will thank you again, Martin, for your presentation and for your answers to the question. And we have one more minute. So Luca, if you want to get ready, can you hear me? Probably.
Yes, I hear you, Nicolas.
Okay, you can get ready. I'm going to get ready as well, and we'll start like within a minute. Your last but not least presentation. So right. Try to share your screen.
Yeah. Do you see my screen, Nicolas?
Yeah, it's perfect. We hear you well. We can see your presentation, and it's 5:20 here in France. So it's my pleasure to introduce Luca Ligny, who is a master's student at École Nationale de l'Aviation Civile, which I know pretty well. He studies optimization and telecommunication, and he is going to talk to you about aircraft emergency trajectory design with different complicated methods that he'll be happy to tell us about. So give you the mic.
Okay, thank you, Nicolas, for this nice introduction. So I'm going to present to you my work that I did along with András Guitar and Daniel Delahaye from the ENAC, and with Benavar Sridhar, who's from the NASA Ames Research Laboratory. My work is about aircraft emergency trajectory design, and I propose that a quick introduction. If you have already seen the movie Sully, you will know what I'm talking about. But for those who don't know the event or haven't seen the movie, I'm going to explain to you what happened. So on January 15th, 2009, an aircraft departed from the LaGuardia airport, and about 2 minutes after takeoff, the aircraft struck a flock of birds, and the aircraft lost all power. So the objective was to land safely. The first solution, so the first emergency trajectory proposed, was to return to LaGuardia Airport, but the pilot assumed that it was impossible because the aircraft wasn't high enough in the sky. Another solution was to land to Teterboro Airport, but again it was impossible. So finally, the final emergency trajectory was to land on the Hudson River, as you can see on the figure on the right. And all these decisions have been taken in tens of seconds. So really, the decision time is really a factor here. So to present to you what we are doing here, we have a situation of emergency, and we know the best landing site already. And our purpose is to generate the best emergency trajectory. What do I mean by best? The shortest one and the safest one. And this trajectory will be computed thanks to an algorithm, which main stakes are the computation time. As I said, it has to be realistic. So the return trajectory must be under a few tens of seconds. The algorithm will work on a flight management system. So the stored data sizes are very important. And as I said, the quality of the trajectory is also important. The trajectory must be short and flyable. To present to you what I'm going to do in this presentation, I'm going to introduce you the mathematical modeling that I use during my research. I will present to you how to optimize the data structure in order for the algorithm to be able to work on a flight management system. I will present to you the algorithms I used, and finally some results that I obtained during my research. So let's go with the mathematical modeling. On this slide, I present to you the free space. So it's empty. Really, the free space is the absence of obstacle. It's the absence of anything. And in this free space, there is an aircraft, and there are some obstacles. In this figure, the aircraft is behind the mountains, and we have a situation of emergency. So we know the emergency start point, and we know the emergency endpoint from which the aircraft will be able to land safely. What is commonly used in aviation is to advise the pilot to make easy procedures because this is a very stressful situation. So the procedure must be easy. And the first idea is to advise the pilot to follow a single glide slope, a single descent plane generated by these two vectors. And we will force the trajectory of the aircraft to stay within this glide slope. Thanks to this, we do not need to save the mountains informations that do not intersect the glide slope, and we require a lot less of information to store our data, as shown on this slide. So on this slide, there is the same descent plane, but with black pixels and white pixels, and this is the only information that will be stored on the flight management system. On this 2D grid, we'll be able to launch our algorithm and to generate a trajectory with the algorithm based on a fast matching method. We will consider two kinds of aeronautical constraints, the radius of turn constraints on the left and the heading angle constraints on the right. The radius of turn constraints come from the fact that the aircraft trajectory must be smooth. It cannot make 90 degrees turns instantly. And the heading angle constraints come from the fact that if the aircraft has lost all power, its trajectory has to go down on the glide slope. It cannot go up. So we can formalize our optimization problem. We have to minimize the length of a two-dimensional emergency trajectory, which is subject to terrain constraints, to aeronautical constraints. And this optimization problem must be solved with a fast algorithm that requires low data sizes. So I will show you how to optimize the data structure in order to make it work on an FMS. As I said to you, all our terrain information is stored on grids with little squares, with black squares and white squares. It is more adequate to store all the data with triangles. With the two figures on the right, you can see the simulation, fast marching simulation of a drop of water on a surface. And you know that it makes circular waves, and these circular waves are better reconstructed with a triangular mesh than with a square grid. So our algorithm will be more precise, and the trajectory will be smoother and will be more flyable. And we will also gain in efficiency. We'll save computation time and store data sizes. Only one condition for our algorithm to work is that all triangles in our meshing must be acute, because the algorithm will not converge otherwise. So how to create a triangular mesh from a two-dimensional grid? On the figure on the left, I showed you a really simple example of 8x8 grid with white squares and black squares. And we will try to optimize this structure by using quad trees. Quad trees have the ability to store in huge cells the information of free space, and by keeping really good precision around the obstacles. The problem of quad trees is that you have squares that are neighbors that have a difference of level, which is important. For instance, on this example, this cell 32 is next to the cell 40, and it has a difference level of 2. It will degrade the quality of the generated trajectory. And to solve this problem, we have to balance the quad tree. What does this mean? It means that we have to ensure a level difference of 1 between each square neighbors. So we have an optimized structure which will be good for our algorithm and which will return a smooth trajectory. On this balanced quad tree, we are able to create a triangular mesh adapted to the terrain using only 6 templates. And we are able to do this directly. We have a minimum of triangles per square, and the condition that I mentioned above is respected, which means that all triangles are acute, and our algorithm to generate a trajectory above this structure will work. So let me present to you the fast matching algorithm. First, I will present to you the Dijkstra algorithm, which is a real simple algorithm, which is very similar to the fast matching, and which will help you understand a lot better what I'm doing here. On this slide, you can see a graph. You have the start node in red in the up left, and in the down right, you have the end node. And so it's the start point and the end point of our emergency trajectory. The color code is important. The edges are in green. They are to remind the triangles of our meshing. In purple, you have the costs, and in dark green, you have the weights of the edges. And how to compute the best trajectory on this graph, you have to start with a start node and to propagate the cost throughout the graph by making additions. So 0 plus 2 will compute this cost, which is 2, and 0 plus 3 will compute this cost. We mark down the optimal direction with gradients, which are represented with orange straight lines. And this means that from this point, the optimal trajectory is in this direction. We continue to propagate the costs throughout the entirety of the triangular mesh until we hit the final vertex. And we compute the optimal trajectory by ascending the gradients. So we start with the end vertex, and we ascend the gradient, and we compute the optimal trajectory. You see that this trajectory is dependent of the graph. This means that if we had a lot more points, we would have a better trajectory. The optimal trajectory on this graph is a straight line, but it cannot be computed because we do not have as many points as we wish. You will see that the fast matching algorithm with the same number of points provides a lot better trajectory and a smoother one. So how does the fast matching algorithm works? It really a good representation of the fast matching algorithm comes from fire forest propagation. So here you have a forest with trees and grass. You have a field at the bottom right and a river at the top right. And a fire starts propagating from the central tree. The fire propagation is circular, which means that it takes the same time to join all the points of the circle, and the propagation continues. And the propagation is a lot faster in the field because the field is not wet. So the isocosts are deformed, they are no longer circular. This deformation is a lot more visible with time, and the fire continues to propagate until it hits the river. It cannot go through the river because water kills fire. And finally, the propagation stops when there are no more trees to burn. And really, it's the main idea of the fast matching algorithm is this notion of propagation. How to compare it with Dijkstra's algorithm? Really, it's the first step is the same step as Dijkstra's. You only have to add the costs from the start vertex to its neighbors. Only with Dijkstra's algorithm, we had an update from vertex to vertex. Now the update comes from the edges. They come from within the triangles. And to compute this cost, we have to take into account this cost and this one, and the update comes from the triangle. So the gradient will point towards the edge from which comes the update, and the cost is a combination of the two neighbors' costs. Again, the propagation continues in the next triangle. So this cost will be updated from its two neighbors, and the gradient will point towards the edge from which it is updated, and so on until we reach the final vertex. So all the formulas to compute the gradient and cost will be presented on the next slide. Finally, to compute the optimal trajectory, we have again to ascend the gradients. And when a gradient intersects an edge, we have to interpolate the gradient from the two gradients that compose this edge until we reach the start point. we see here that we have a very better trajectory, a smoother one and a shorter one. So this is an interesting algorithm. What's the concrete, the real update procedure on a triangle? So here we have a triangle ABC with a cost at A which is lower than the cost at B, and we have a front that arrive on this triangle. So remind the fire forest propagation, which was circular. It's the same here. One front is going to hit vertex B, and for algorithm purposes, we are going to linearize this front. That is to say that this circle will be considered as a straight line in this triangle. This is called an isocost. So the update procedure to compute the cost at C, it's very simple. We only have to take the cost at G and to add the distance between the points G and C. The direction of the gradient will be the direction of the vector GC. It's a very simple update procedure. And for the back propagation, when we start at a point C, we only have to ascend the gradient that was computed during the propagation phase. And as I said before, the gradient might intersect one edge, and we have to interpolate the gradient from the gradients that compose this edge with the interpolation parameters that is written below. So I'm going to present you the results, how this algorithm works, and the performance that we reach. So I hope you can all see my video. So this is the Grenoble mountains, the 2D descent plane. We have built a quad tree on this 2D grid. And as I said before, we are going to balance this quad tree. That is to say, ensuring that there is a difference of level of 1 maximum between two squares. This is a code to retrieve all the neighbors of the squares. So this code starts at 0 at the top left, and it goes down, making these throughout the entirety of the grid. These are the level differences, and we have ensured that there is a maximum 1 between all neighbors. On this structure, we are able to create a triangular mesh using the same templates as we presented before. And we have succeeded to create a triangular mesh, an optimized structure on this 2D grid, on this descent plane. Here you can see the emergency start point in red, and in blue the vertices of the graph. And the fast matching algorithm computes these gradients in orange, the same ones as I presented before. And for instance, on this particular vertex, the fast matching algorithm computed a cost of 5.6 and a gradient direction, so an optimal direction from the start point in this direction. The gradients and the costs are propagated throughout the entirety of the grid until they reach the endpoint, so the end of the emergency procedure. And we can now enter the back propagation phase. So we start at endpoint, and we are going to ascend the gradients and interpolate the gradients as we intersect the edges. For instance, on this point, this gradient was computed from this tube and it was reversed in order to reach the start point. This procedure ends when reaching the start coordinate, and we have generated the optimal trajectory that avoids the obstacle and which respects all the constraints. So a little bit of analysis of our work. So on the right, you can see the trajectory that was generated just before on the descent plane. It only took 0.5 seconds to generate this trajectory with a fast matching algorithm. But it was an easy scenario. But for most scenarios, the computation times remain under 1 second. All structures embedded on the FMS require less than 1 megaoctet of storage. So it is possible to make it work on an FMS. Trajectories are flyable and they avoid the obstacles and they respect all the constraints that we mentioned before. To provide some limitation for our model, we assumed that we were able to create directly a single glide slope. That is to say that the airport on the base landing site was between the max descent and the minimum descent rate of the aircraft. But there is a scenario where the aircraft is too close to the base landing site and it cannot generate a single glide slope directly. It has to lose altitude to be able to generate such a descent plane. So we designed some procedures to be able to tackle such problems. If the aircraft is too close to the base landing site, we will advise the pilot to make waiting turns in order to lose altitude. So these turns are computed with Dubin curves. Dubin curves are just straight lines and arcs of circles until we reach a point in space called start coordinate, from which the aircraft is able to land using a single glide slope. On this slope, we are going to use the fast matching algorithm. There is another problem when the aircraft is not well oriented with the base landing site, and we can also use the Dubin curve to conceive an approach procedure to help the pilot reorientate the aircraft and to land safely. So here comes the conclusion of our work. So in our paper, we were able to establish the aeronautical constraints over a single glide slope. We were able to build a memory space friendly structure for the terrain. We implemented the fast matching algorithm over a triangular mesh. And finally, we defined procedures when the direct generation of a single glide slope is impossible. Let me present you some future work. So we have in mind to test the algorithm with multiple glide slopes generation, because it will allow the algorithm to be more realistic and to provide a better solution in more scenarios. We also have the idea to build a three-dimensional method. So I just finished my end of studies project at the ENAC, and I developed the equivalent three-dimensional method, and it gives interesting results and promising results. We could also take into account the wind constraints. So again, I did this in my end of studies projects, and it works pretty well. And finally, we can test the algorithm on real scenarios. For example, return a solution for the flight 1549 and see if the algorithm is able to ensure a safe landing for the aircraft. I thank you all for your attention, and I remain at your disposal if you have any questions.
Well, thank you, Luca, for your presentation. So to the audience, if you have questions, you can write it down in the Q&R, the discussion. You can raise your hand. I'll be happy to give you the mic if you want. While you're doing that, I will ask you a question. So you were saying at the end of the, well, first of all, I will say I found that your presentation was nice and very, you explained very in detail the algorithm, and that was very interesting.
Thank you.
So, and now at the end, you come up with some issues that you had. Can you come backwards to your
Of course.
when you
Maybe.
here, that's an interesting point. So, of course, the whole problem is that if you're too far from a runway, then you can't do much. You'll have to choose another runway or another. That's what
exactly,
happened.
yeah.
That's what happened in New York. And if you're too close, you're going to have to waste some time or to try to get further from the runway. And you were talking about doing a 2-minute circle, or well, doing a circle, for example. So those circles are generally like 2 minutes. You can make it a little faster, a little slower, but you cannot make a circle. And it's a discrete amount of time. It's not like an amount of time that you can choose. Have you considered what kind of constraint it adds to your problem?
Mm,
Maybe
not really, no.
okay. Do you the second question is like how you said like on real problems the FMS computer was able to deal with your problem in less than a second. When you do such research, you want to stress your algorithm to see to what extent it works and after what extent it doesn't work. Have you done tests to see how big of a problem would make your algorithm not work anymore?
Yeah, basically, the computation times are really linked with the precision of the stored data. That means that if we have a lot of points to describe the space, the algorithm will take much longer to converge. And it is always possible to take huge grid steps, for instance, to lessen the data sizes, but the quality of the trajectory will be damaged.
Okay.
So we are always able to return 1 second trajectory. For simple cases, for simple scenarios, as the one that I presented, we have a really good trajectory is returned. But maybe for more tricky scenarios where there are more mountains or we have a longer descent, it will be interesting to take bigger step sizes to lessen the computation times. But
Okay.
we are always able to manage the 1 second gap.
Okay. And your algorithm works from the backwards from the end to the origin. Is that correct?
Yeah.
Okay. Is it possible to make it work both ways?
In fact, there are two phases. The first phase starts at the start point, and it propagates throughout the entirety of the grid. So this is in one direction, and the back propagation is already in the other direction. It's not we do not have the information at the start point. They always come from the endpoint to generate the trajectory. So it cannot be be done from the start point.
You cannot reverse the problem.
Yeah, it's we can reverse the problem. It's only the optimization from a point A to a point B. So yes, the problem can be
same from B to A.
Yeah, of course, but we cannot win time. We cannot save time.
You cannot like try to meet in the middle.
Yeah, exactly. Yeah.
Like you can do some other algorithm where you propagate from both ends and you try to reach in the middle.
Yeah.
That doesn't work. I haven't thought about it, but on other methods, sometimes you can like.
I think really this could work, but it doesn't really save time because the same number of points are to be reached. So I don't really know.
Okay. So now we have questions. Great.
Oh, great.
So
Thank
Marie Carré, who thinks your presentation was really interesting, would like to ask you what would be the optimal trade-off between trajectory quality and computational time, especially like in complicated fields such as the Alps. So how would you make the trade-off? Like you would, it's an interesting question, like how, if you decide to do a bad solution but very fast, is it worth doing that first and then refining if you have more time? What's the amount of time of you use if you divide by 2? If the size of the grid is 10 times bigger,
Yeah.
And does it how do you make the trade-off? Yeah, that's the problem.
Oh yeah. So basically, we used the 1 second threshold because of all the constraints, the real-time constraints in an emergency situation. So the 1 second was, we had the idea that we could use the algorithm multiple times in order to evaluate the different scenarios. For instance, if we know 3 best landing sites, we know that we only need 3 times 1 second to have the best solution, but to have the 3 different scenarios of trajectories. Now, the fast marching algorithm has a complexity of n log n. So it means that if you have, I don't know, I won't be able to make the calculations here, but basically, it's because we have an optimized structure. We do not need a really precise grid. I don't know if I can give you, if I give you figures, I might be wrong. So I don't really know how to better answer this question.
Okay, well, you tried. Well, sometimes we don't know the answer. There's a lot of questions about how, like, for example, do you need to know the emergency landing site to compute the trajectory?
Yeah.
Can you start from the selection of the best landing site? Can you select the best landing site before you calculate, or can you, is there a way to do a selection? Maybe
in fact, this project was part of European projects, so there was different entities, and one entity was its mission was to select the best landing site, and our mission was only to generate the best trajectory. Okay. But once we have decided which was the best landing site, our algorithm run once. We cannot. We have to rerun the algorithm in order to consider another landing site.
Yeah. Okay. And there's another question from Diogene de Souza, Heathrow. Hi, Lucas. This is a great piece of research from an implementation perspective. Does the terrain data come from the onboard terrain alerting system, or does the FMS need to have a database of terrain data? That's a very concrete question.
Yeah. In fact, we had some ideas. We did not really. What do I want to say? We did not really tested it on an FMS, but we thought that the aircraft would be able, thanks to forward-looking radar, to retrieve the terrain information, or maybe if the aircraft already loads the terrain information before the flight, we would be able to have the terrain information already embedded in the aircraft.
And also to come back to your first to the movie, the famous movie,
Yeah.
Sully. The question is that what if you don't have any landing pre-selected landing location? Like, can you comment on non-standard scenarios where the end of point cannot be known? Like, they ended up in the river, and the river is not a landing area. It's not supposed to be a landing area. So what if, like, Sully had pushed the button and say, well, you have to go there, but like there was no way he could go anywhere, and what would your algorithm would answer?
Yeah, of course. With our two-dimensional algorithm, if the Hudson River was not considered as a landing site, it wouldn't have given the solution, of course. With a three-dimensional algorithm, I didn't really explain it in this presentation. Thanks to this propagation, we are able to generate a lot of trajectories that are independent from the landing site. And we are able to generate such procedures to land on the Hudson River, but it is impossible with a two-dimensional algorithm, because the generation of the descent plane depends on the endpoint of the trajectory. So we have to already know it beforehand.
And are you going to continue this research? Are you doing
yeah,
a PhD?
I already continued it during my end-of-series project, and I don't know, maybe for fun, but no, not in a PhD thesis.
Okay. Well, thank you very much. Is there any other questions? So if there is no more any questions, you have to rejoin the plenary session for the end of the conference. That's the best paper session and all the concluding sessions that you can attend right now. If you use the link that is well, that you know now. I don't know which link it is. Somehow in your email, there's a link, and you go back to the plenary session. And thank you everyone for your attention, and thanks for the presenters and the really interesting debate we had all together. And let's hope that next time we won't have to do this on Zoom, and we can like share more than written questions. Thank you, everyone. See you soon.
Thank you, guys.